Okay. All right, so here's where we finished off on Monday. To kind of recap where we were looking at designing a lag controller, and keep in mind, lag controllers are for the purposes of improving steady-state response. So they're analogous to a PI control design, improving steady-state response. So here we had a condition where we wanted to have the steady-state error to a step reference to be less than 1%. And we went through and we leveraged the content from lecture 12, which talks about steady-state errors, to understand what this single parameter in our lag control should be. And we said that approximately should be greater than this alpha, should be approximately greater than 21. And so we said, just for good measure, we'll make this alpha design variable 22. So the reason why we can't just say greater than 21 is a design for a controller, because you can't write a program that says make this number greater than 22, right? You have to pick a number, or 21. So you have to pick a number, so we picked 22. All right. We also talked about how when you add a lag controller to your system, you do not want to improve the transient performance that's already favorable. And so the question is, how do you do that? And so we have to have a pole and a zero, where the zero is 22 times as large as the pole, but also we evaluate the angle criteria for the root locus, which determines the transient response. We want the contribution from the angles from the zero and the pole to essentially cancel each other out, so it doesn't distort the root locus plot any. And so the way in which you can do that is we're going to put both the pole and the zero very, very close to the origin, and have the zero 22 times as large as the pole. Right? And so now, what do I mean by very, very close? This is kind of, there's no real answer for that. It really depends on the dynamics of the system, right? So if you're talking about, say you work for Motorola, you're building feedback control loops for their cell phones that are electronic devices, your poles in an electronic device are going to be much, much faster than if you're designing a control system for the temperature control in a room, right? So the time constant associated with electronics is so much faster than time constant associated with the thermal response of this room. Electronic devices are on the orders of kilohertz, megahertz, et cetera. And in the room, we're talking about time constants on the order of hundreds to 200 seconds or something along that line, right? So very different time scales. So I can't give you like this general rule that's going to work for everything, but we can kind of pick some spots and see how they change then the total response of the system. So if we look at what we have in our system, and I'd have to go back, there we go. I think it actually makes sense for me to pull this up in software here. So let me just enter in this transfer function really quick. Okay, so here's a transfer function for our system. Let's double check that really quick. Looks good. So I'm going to pull up the root locus plot, and we're going to just take a look at what we have going on here in terms of dynamics of our system. So this, remember, had 4 poles, 2 zeros. So we have this shape for our root locus plot, and we have basically we have a few things going on that we could look at with what's happening here. So we have a root locus plot that looks like this, but we have a few things that we can see. We have the closed loop poles, which are these pink dots. We have essentially a pole zero cancellation here, and we have a pole zero cancellation here. And so these are dynamics that are not really appreciably affecting our system. The system is acting like these 2 poles here and here for the most part, right? Because these are the ones that don't have a pole zero cancellation. They're fairly close to the origin. These are being canceled. So if we look at what is kind of the dominant dynamics of the system, they are somewhere on the order of natural frequencies of 10, right? So if we look at, if we were to draw an arc of 10, that would be something that's kind of going around here, but it's a little bit larger than that. These are a little bit outside that. So just kind of rough order of magnitude, somewhere around natural frequency of 10 is the dominant dynamics of our system, right? Because these ones are canceled. And so kind of a rule of thumb is make the dynamics of your lag controller, at least the 0, to be about 10 times less than that, right? So if we want to be sufficiently away from the dominant dynamics of your system, somewhere around an order of magnitude smaller. Right. So the reason why an order of magnitude is a good kind of rule of thumb here is if you look at the lead controller or the lag controller, and you'd have the phase associated with a real pole or a real zero, that spans a decade to the left and a decade to the right in terms of how the phase changes. So we want basically the influence in terms of the frequency band to be about an order of magnitude smaller so that it's not causing any phase distortion in our system, is the main rationale behind this. So just to kind of note, dominant dynamics here, these aren't really that important. So we're going to be putting our lag controller dynamics all within this region. So we're going to select our 0 for our lag controller to be around 1. That's what we're going to start with. So just kind of typing that out in text. So understand the dominant dynamics of your system. Here are the dominant dynamics. Have a natural frequency of approximately 10 radians per second. Choose 0 location to be about 1 order of magnitude smaller. Then there's dominant dynamics. All right. So the transient, that's basically the shape of the root locus. We're trying to not affect the transient response. We're going to make sure that our dynamics are sufficiently slower than everything going on for the transient response of the system. So for this example, we're going to choose T, which we go back, just to remind everyone, the form of the lag controller, wherever that went. All right, so this is going to be the form that we're going to use here. So it has alpha gain out front. The 0 location is at 1 over T, and the pole location is at 1 over alpha T. So for this example, we're going to make T is equal to 1. All right, so that means that the 0 location is equal to 1. And then we're going to have, that means alpha T is equal to 22. So that means that the pole location is equal to 1 over 22 for this particular example. Sorry, I forgot to remind everyone then also, so the reason why we're trying to improve the steady state error here is that we said that, okay, the transient response of the system was appropriate as determined by the specifications given in the problem statement. So the overshoot in the rise time was perfect or within limits. And then the deficiency in this controller was that the steady state error was too large. So we want the steady state error to a step reference, a unit step reference, that means a reference of 1 to be 1%. So we want this E final value to be greater than 99.99 here. Right? We're currently around 0.82 for this. All right, so we selected alpha to make sure that was true. So now we have a design for a controller. So if we look at our lag controller, so we have G1 lag of S is going to be 22 S plus 1 over 22, 22 S plus 1 will be our lag controller design. So given what we did on Monday and also today, right? So this problem spanned 2 lectures. Okay. So given this design, we can plug this in to MATLAB. So here we have a Locus plot. I'm going to add dynamics to the controller. It's going to default as 1. I'm going to add a lag controller. Okay. So let me actually just delete that for a second so you can watch this in real time here. Okay, so going back to where we were. So this was the root locus plot for just proportional control with a gain of 1. We said that transiently that's sufficient, right? So we're good there. And what we're trying to do is we're trying to add a lag controller so we're not sufficiently distorting this root locus plot here. All right, so when I add this lag controller, it's going to put it in the default variable or pole and 0 location for lag. So it's going to temporarily distort the root locus plot, but just kind of like burn this shape into your mind here for a second and see if we get, after I do some manipulations, get back to where we started here. So I add a lag controller. All right, we said that the 0 location is at 1, pole location is at, yeah, it doesn't allow me to do math. What's 1 over 22? There we go. It's, yeah, thank you. Okay, and I don't know how well we did. We'd have to like compare the plots right on top of each other, but essentially this does not change the root locus plot any. If I crank up the gain to 22, which is where we said we want it to be, we see a few things that are common from our discussion we just had. So we said we had a pole 0 cancellation here, right? And then we also had a pole 0 cancellation with this pole and then the pole from the plant, which is approximately -1. And then we had dominant poles here and here. Right? So we've added the lag controller. Basically the same thing is true. What has changed, though, is that we have added an extra branch of the root locus because we've added a pole that's added a branch to root locus. We can take a look at this branch. Zoom in a little bit. Okay, so I've added a pole here and a 0 here, given by the red circle and the red X. We see that the close-up pole here is getting kind of close to this 0, so it's approximately a pole 0 cancellation. And so then we can now say, all right, we haven't distorted the root locus considerably. We can now take a look at our response, and what you'll notice is that some things are, the step response looks pretty much the same. All right, so we haven't, it's changed obviously, and actually the overshoot's reduced a little bit. But we haven't appreciably changed the transient response, but now we are going to a higher level, right? So before, we were going to 0.82 on this step reference, and now we're getting almost to 1. Right? So what we've done is we've improved the steady-state response system. We haven't changed the transient response system. So lead lag control design, which you have to do in your project, you want to do the lead first to get the transient response to be appropriate, then you do lag to take care of the steady-state response of your system. Right. Any questions on that basic design procedure for lag control? Carson?
Well, it's not as obvious where the dominant natural frequency is.
It's not as obvious? Okay.
Yeah, like there's like a couple of them that are all close to zeros.
All close to the origin, you mean?
Like you're taking just the flat by itself, and then once you got the transient response you're looking for, you still got two imaginary poles, or two sets of imaginary poles that are close to being eliminated.
Yeah.
Like you take average of those two, you take one.
Yeah. So if I understand you correctly, say for instance, I were to so if I were to get rid of my lag controller, and then say I make this like this example here. All right. So this is where it gets into what I say reading tea leaves. Gets a little bit more complicated to do, right? So in the case I gave you, you had the pole zero cancellation here, right? So I made sure these are clearly canceled out. And we had pole zero cancellation here. You see this is actually still fairly well canceled. But now what you're competing with is you have these two complex conjugate poles, and you have this one that's fairly far away from this zero. So the question is, which one is dominating? So I haven't done this one. I've never looked at this before, but I'm going to guess that this one is going to dominate because this is the pole that's closest to the origin. Right. So now if you have a bunch that are all equidistant to the origin, you'll have to take a look at that and see what's going on there and look at the rules in terms of how when you add a pole to the system, how that changes the response. But this is going to, for the most part, act like a single real pole, which is going to act more like a first order system. And then I say that, and we'll check my response here. I don't know how well my guess was in that one, but it doesn't have a ton of oscillations in it, so you don't see a dip, right? So it's acting a little bit, has a little bit of overshoot, but it's fairly, it's a somewhat first order in nature, but it's kind of a combination between these, right? So I would say it's really like reading tea leaves. I think it is, and so if you look at root locus is usually how we introduce this idea to undergrads first learning this, because it works for, I would say, fairly simple systems. This is fourth order, and so now we're kind of pushing the limits of where root locus really, you can get a lot of good information out of this. We'll be talking about, at the end of the day, starting getting into frequency domain tools. Those are usually used for more complex systems, because they're a little bit more, it's not so wishy-washy in terms of how you read these. But here we would say that we have a pole here as well that's going to have an influence, where before it was canceled. I don't know if that helps, but so kind of to comment on that a little bit farther, maybe is a good prelude to the frequency domain response methods. If I put this back to 1, which is where we started, right? So we get cancellation, cancellation, right? And then we have, if I look at my Bodie plot, when you have pole zero cancellations in the open loop, it really makes it much easier to interpret what's going on, because it's just easier to see these cancellations in the frequency domain. So for instance, these are a pole and a zero that have the same frequency, but these wouldn't necessarily have to be, if they're complex conjugate poles, they could be at different regions because they have different damping ratios. And so it really helps you try to understand how the major effect of this will be. And so this pole and the zero, they essentially, there is no effect of these. This, you can almost draw a straight line from the left of this pole and zero to the right of it, right? So you can really clearly see how they cancel out. We'll go into this in more detail in the next coming lectures to talk about this, but Locus plots I think are really good for systems of about 4 poles and less. And once you get beyond that, it gets pretty confusing to try and read what's going on, in my opinion. Yes?
So could you just briefly go over again how you chose T? Because I understand. So did you just pick one that was like to the right of your other poles and zeros, so that way it wouldn't affect the system much when you cancel it out?
So I took a look at this and said, okay, so pole zero cancellation here. So remember the closed loop poles are the pink dots here, and then the open loop poles are also the same as the open loop zeros are also the same as the closed loop zeros. That's going back to a homework problem we had a while ago. Basically, if there's a zero in the open loop, it becomes a zero in the closed loop. Right. So if we look at here, we have a pole zero cancellation from a closed loop pole and a open loop / closed loop zero, same thing. Right? And we have one here as well. These are really close to each other. So we're saying the system mostly responds like these complex conjugate poles here. And this has about, as rough numbers, a natural frequency somewhere around 10. It's a little bit larger, but. And so the rule of thumb is kind of to make the zero of your lead or your lag controller to be an order of magnitude smaller than that. Okay. And so this is, so if I were to look at this in the frequency domain as well. Okay, so this is how the system behaves without adding the lag controller. And then if we look at what a lag controller does in the frequency domain, it has this shape where the purpose of this is to have essentially no effect at higher frequencies. So this is higher frequencies, has 0 dB magnitude, 0 phase. So what we're doing is we're adding features to the frequency domain that has a high gain at low frequencies and then also this phase lag at low frequencies. So if I look at the Bodie plot for the system, I add back in my controller. What we should see is we're not going to affect the Bodie plot in these high frequency regions. So it's maybe a little bit tough to see all that moving around dynamically, but you can see the pole I added from the lag controller and the zero I added from the lag controller, those are given in red, not blue. And so the dynamics of what I added is pretty much only in the low frequency region, and I haven't affected the high frequency region at all, which is how so basically low frequency is a response to steady state, response, high frequency is a transient response. So everything I'm doing, I'm only affecting low frequency. Okay, so also just like it was discussed in PI control, it can be used to project disturbances. So I showed the example, I have the system on my desk up here. I showed that if I were to go take my hand and start to just crank on the inertia, that would actually fight me. So same idea, that was PI control would fight you. Same idea with lag control. It can be used to counteract some sort of disturbance. So a disturbance is, well, the definition that is, we'll say, very wishy-washy, but a disturbance is any input to your system that is unexpected and or unknown a priori. Okay, so what I mean by that, so for instance, I have the system sitting at my desk, right, has this inertia, and I just came up and kind of took my hand on it and put a torque on the inertia, right? So that'd be a disturbance because it's some unknown torque. I don't really know how strong I put it in terms of put a torque on the system. And it wasn't expected to. The system is just a computer. It has no knowledge that I was going to go and add this disturbance to the system, right? I knew I was going to do it, but the system itself did not know that, right? So the project statement, right? There's an example of what happens if someone were to hang, I think it's like 3 kilogram mass off of it, right? So that's just say hanging, but also say you have an assembly line and you're picking up things and you want to be able to make sure this controller moves well, whether or not it's picking up nothing, just moving around in space, or it actually goes and picks up something that weighs 3 kilograms, you still want to have good performance. Or another example would be cruise control in your car, is that you want your cruise control to work no matter if you're going on a straight section of road with no hills, or you want to maintain your speed if all of a sudden you hit a hill, you want to be able to still maintain that. So the car has no idea if there's a hill coming, right? It's going to be a hill of unknown grade, so you don't know how much actually the force going back down the hill would be on your car, and you still want your cruise control to maintain that same speed, right? So these will all be examples of disturbances. Also wind on a car too is very unknown, but you want your car to still maintain its performance regardless of what's going on around it, right? So what the lag control allows you to do is it allows you to reject steady disturbances to your system. A hill is fairly representative of a steady disturbance as long as it doesn't change its grade all that quickly. Picking up a mass, that's a steady disturbance because that's now just adding mg in terms of force that the system has to basically pick up. So those are all kind of examples of disturbances. But it's basically anything unknown, unexpected that could happen in your system. You want to be able to be robust to that, right? Just to be able to maintain performance. So the way in which we model this, and this is going to be important for your project, is we have, I'm showing one type of disturbance here. This is what's called an input disturbance. All right, so what we have is we have our typical feedback loop. So this would be our typical feedback loop. All right. And so what we're saying is that if we want to model this disturbance, if we have some idea of what's going on, we can say this disturbance, W, goes into our system. And it could potentially have some sort of filter or transfer function before it goes into our system. I think I'm missing a plus sign here. All right. And then it enters our system in this way. So with this, we would call this an input disturbance. There's some sort of input into our system that's going to affect the final output, and it comes in this fashion. Right. And so what we're typically looking for with steady-state error is we're looking at how does this reference affect our steady-state error. So that's coming in one location in the block diagram. The disturbance is coming in a different location, right? So the transfer function associated with it is going to be different. So I'm just going to quickly show what that transfer function would be. And this will be, I would say, very important for finishing the part of the project where we're trying to understand what happens when you put a mass on the robotic system. Is you have to consider that it gives you two steady-state error requirements. One is for a change in reference, and one is for a change in mass. Right? And so you have to make sure that your controller can be robust to both of these and have an error below the specified threshold for both of them. So if we look at what is this transfer function C, all right, so C right here is going to be equal to G2 times the quantity, this is E, right? G1 times E plus G3 times W. And then if we say that E, the error, is equal to R minus C, then I can rewrite this as C moving everything that is a function of, let's see, what do I want to do? Yeah, everything that's a function of c over to the left-hand side. That's going to give me 1 plus g1, g2 is equal to g1, g2 r plus g2, g3 w, and then solving for c, has this format. Okay, so before everything we've done thus far in this class, we've only looked at this transfer function. And this is going to be a new transfer function. Okay, so this just looks at how this input, our disturbance, affects the system. That's different than how the reference affects our system. Okay, so when you're designing your controller, you need to make sure that the lag controller for this, you need to make sure you can reject any influence of this disturbance to the system. To note, denominator for both is 1 plus G1, G2. Right. And so stability of our system is given by the poles. So that's the values of S such that 1 plus G1, G2 is equal to 0. So basically if you design your system so it's stable for a reference, which is a lot of what we talked about thus far, it's going to be stable for a disturbance because it has the same denominator, right? So if you establish that stable for the reference, you don't have to worry about stability for the disturbance. It's going to be the same. Okay, and then lastly, if I want to know, this tells us what the output is as a function of this disturbance W. If I want to know what the error is, if I want to understand steady-state error, again, E is equal to R minus C. That means E is equal to R. Inserting C into this equation, G1, G2 over 1 plus G1, G2 R minus G2, G3 1 plus G1, G2 W. So these will combine here, and then that will give me 1 over 1 plus G1, G2 R, which is what we did before. This is coming from lecture 12 when we derived this, plus then, minus G2, G3, 1 plus G1, G2. All right. So this transfer function, important for project. Okay. All right, and then very last thing on this lecture before we move on to new content is lead lag control design. I will address this briefly on Monday, and I'm going to address it briefly here as well. Lead lag control, there's no real mystery behind it. It's pretty simple, but we have that G1 lead lag of S is equal to K S plus Z1, S plus P1, S plus Z2, S plus P2. And then we have the constraints. So we said this is the lag. This is the lead. And then we'd have the constraint that we have this sequence of zeros and poles for our system. So no real mystery. Design the lead. Make sure that's good. Design the lag. You just combine them together. That's your combined controller for your system. Yes?
When you're designing the lag, do you take into
So that's a good question. So because you have to design a lead lag controller for your project, right? So say for instance I have a plant, right? Just as kind of an aside example. Yes, this is our plant. It's just whatever. We'll just make something up, right? And then we have G1 lead, so you have this, and you are really happy with it. It's an awesome controller. Right. And so then I think you're asking how do you determine this value alpha, right? What's this, right? So keep in mind that alpha, you are looking at a transfer function. You're trying to understand what is the steady state error for the system for given that you have G1, G2 identified, right? So we've done half of G1. We've just done the lead section here. So what you're saying that G1, G2 is going to be equal to is this unknown transfer function yet, alpha TS plus 1 over alpha TS plus 1. So this is quantity, right? This is your lag. You have your lead already defined because you built this and it works great. Right, and this would be the transfer function you're evaluating when you're evaluating the steady state error for the system. Right, because you have to include the lead controller definitely has dynamics, and it definitely has a gain to it, and you want to make sure that you're reflecting that when you design your lag controller. Step 0 of the lag controller is okay. You are already happy with the transient response, and if you required a lead controller, it means that you had to do some work to become happy with that transient response. So you have to include that in there. Okay. Any other questions about any of the content that we talked about in terms of design here? All right. On to the next lecture. Okay, so about 15 minutes or so. Okay. So just to note, I have handwritten versions of this already. I can post those, but they're a little bit messy. So I'm working on turning these into actually type notes. So there's good quality as all the rest of the control stuff. So it's still, we have enough to get through today, but there's not a full note set there, just for your own personal knowledge there. But more than enough to get through today. All right, so what we looked at thus far was root locus methods for design and analysis of controlled systems, and we talked about how understanding these, especially when you get complex systems, a little bit like reading tea leaves, and gets a little bit complicated. And so you may ask, okay, which way is better? Or which way is better for more complex systems? And myself, and I think a lot of other people would argue that frequency domain methods allow you to understand complex systems in a more intuitive sense. So it's going to basically allows you to see cancellations between poles and zeros much more easily, because that turns into bends in the magnitude or phase, and then those bends cancel each other out when you have a pole and a zero really close to each other. All right, so we're going to go through and talk about this, and a few weeks ago, actually like a week ago, I mentioned that there was someone from Boeing here, and I asked the question because he actually teaches at WashU in St. Louis as well. Person, and I asked, okay, for Boeing engineers, do you prefer them to know root locus methods or frequency response methods? And he said both, but the frequency domain methods are by far what they use the most for their complex systems they have at Boeing. So I try and get to the root locus methods as quickly as possible such that we can get at least a decent amount. Unfortunately, you have to know root locus methods kind of to get to the frequency domain method. So I've been trying to get through as quickly as possible to get to what I consider to be some of the more important tools. But this is also encroaching on more graduate level controls as well. So just to note, for everyone's kind of knowledge, Ohio State our department's a little bit unique in that we do teach controls to undergrads. For the most part, this is a graduate topic or technical elective for a lot of other universities. So it's not like you're behind because I wasn't able to get through all the frequency domain methods. I'd say compared to a lot of other schools, you're ahead. But I have tried to consciously get to this stuff because I think it is more important for industry, especially for really high-tech companies like Boeing or SpaceX or what have you, right? So that's kind of just an aside. The reason why you have to know root locus methods is you have to understand this first concept, actually, which is if, say, for instance, you have some sort of plant, right? And we've talked about this a lot. We have, so given a controller / plant, which is given by G1, G2, the root locus is the set of all values of S such that 1 plus kg1 G2 of S is equal to 0 as k goes from 0 to infinity. All right, so this is taken directly from the previous lecture. And so what this means here is if I have some sort of system, this is just a dumb example for some sort of system. My controller and my plant, I can lump into G of S. This would be G1, G2. I would have this structure here, and I would look at my root locus plot, and I could understand stability, and I would say that I have marginal stability when this K is equal to this K critical. In this range, I am stable, and in this range, I am unstable. Okay, and so the value of S, in which you have marginal stability, S is equal to I omega when we have marginal stability. Right? So this at the cusp between going from stable to unstable, we have to go through a point where S is equal to I omega. Right? All right. So where in what you've learned in 3260 and this class have you made the substitution S is equal to I omega? When do we do this? Bodhi plots, right? Exactly. That's our standard substitution. S is equal to I omega. All right. So what this actually tells us is that by substituting S is equal to I omega, we can actually understand something about stability. That's what we're going to talk about here. So the Bodhi plot can actually give you information whether or not the system is stable or not. Right. Which is something that we always talk about. This is a responsive system to harmonic inputs, and that's definitely true. But there's also other uses for the Bodhi plot as well, and so we're going to use this to understand stability. Okay, so just kind of some notes on this. So polynomial in S to evaluate closed-loop stability is 1 plus G1 G2. is equal to 0. That's in the denominator of a closed loop system. Okay, so the other thing to note is that we know the marginally stable state case happens at S is equal to I omega. All right, and so if we look at this, this is the marginally stable case. And so what we can say here is that we know that 1 plus G1, G2 is equal to 0. That's how we evaluate stability. And then if we insert S is equal to I omega, then what we're saying here is that we want to understand when 1 plus G1 of I omega, G2 of I omega is equal to 0. Or I can rearrange this equation, and I can say, I care about G1 of I omega, G2 of I omega equal to -1. And so when I look at this in a complex plane, -1, right? So what I'm saying is that I have marginal stability in the instance of when G1, G2 is a vector going from the origin to the point -1. So this is marginal stability. So if I ever have a situation in which I evaluate G1, G2 at I omega, and this is equal to -1, I know that the system is at the brink of instability. And so alternatively, instead of saying this is equal to -1, I can, just like with a locus plot, I can say this is the criteria that the magnitude of G1 I omega, G2 I omega is equal to 1, and the phase of G1 of I omega, G2 of I omega is equal to plus or minus 180 degrees, because the phase angle of this vector is plus or minus 180 degrees. Okay. Any questions on that basic concept? That's going to be the main concept that all of a lot of this work in terms of stability analysis is going to be based off of. Yes, Carson.
What are the criteria then for the unstable, like in the same format?
Yeah, we'll get to that in a second. I was actually going to take the rest of today and probably Friday to go through that. But yeah, this is just marginal stability. So this is when you're on the brink of going from stable to unstable. It has to go through this point. So, well, the first part of your question is we'll get to right now, actually. So what this tells us is it gives us the stability criteria, and then we'll talk about why this is unfavorable. And I'll call this, for lack of a better term, clunky stability criteria. So this gives rise to stability criteria that this is our marginally stable point. We can have two different conditions. Is that if we have G of I omega, G2 of I omega less than 1 at the phase of G1, G2 is equal to plus or minus 180 degrees. This is stable. And then here's the if increasing the gain, okay, I don't know why we have a delay all of a sudden. If increasing gain K destabilizes the system, And then the other one, magnitude of G1 of I omega, G2 of I omega, greater than 1 at G1, G2 equal to plus or minus 180. This is stable, which is opposite of what we said in 1, if decreasing the gain destabilizes. The system. Okay, so you can see why this is not the best criteria, right? For one, it requires that you know how the gain affects the system, right? So just in the last minute, we'll obviously improve upon this on Friday's class. This is not a good example. Let me try and find, let me add. Okay, so just leveraging our example from before, I'm going to add just a pole. At the origin. Okay. For some reason it's acting slow. Okay. So this is CISO tool, and you may have noticed this before, but this is the Bodhi plot for the system, and it draws these lines at negative 180, and it draws a line at 0 decibels, which is equal to 1. So that's why it's drawing those lines on there, because that is a stability criteria. So looking at crossover points of when it basically crosses a magnitude of 1 and a phase angle of 180. That's going to be one of the two terms stability. We'll talk about this more on what Friday's lecture. And then what I want to point out here is that right now this is saying it's an unstable loop. So if I were to look at the step response, blows up to infinity. Locus plot, poles in the right half plane, right? And if I were to decrease the gain a little bit, it gives me my cursor. So that means I'm dragging this plot down. I did a little too much. Okay, so now you see it's gone from unstable to stable, right? And the marginal stability point is when we have a frequency. So you can kind of see this. I'm not exactly on it. A frequency which the frequency equals 180, negative 180, and 0 at the same time, right? So that's our marginal stability. That's when I cross over from being stable to unstable. And this you can see, not exactly, but my closed pole locations are on the imaginary axis. That's the marginal stability point. All right, so that is the point which we're going to care about on the Bodhi plot, is those two crossover points. 0 dBs and also 180 degrees, or negative 180. All right, more on Friday.